So again, as to the waveguides, we have normally this dimension something in between 1/2 wavelength and the full wavelength. That's because we want only one mode to propagate, and that's the basic mode TE10. Now let us switch to naming the modes and to talking about them. We've already noticed that there are two kinds of modes. One of this kind is a set of modes that do not have any non-zero component in the direction of propagation as regarding to electric field. Those are called transverse electric. Transverse, I mean, those electric field lies only in the cross-section of the waveguide. There is no component along the propagation. Well, the magnetic field has also component in the direction of propagation. So this is a transverse electric. And as the opposite, we have also transverse magnetic waves, which do not have a component of magnetic field in the direction of propagation. We call them TE or TM. Now with transverse electric mode, there must be at least one of the indices non-zero. So we could have a TE10 mode, which means there is 1/2 wavelength of the standing wave over this longer dimension, or we have TE01, which would require higher frequency but could exist any, and it is just turned 90 degrees, so there will be 1/2 wavelength within this direction. Now there are fields that are less imaginable, like transverse electric 1,1, which would have 1/2 wave this way, but also 1/2 wave this wave. And of course there are modes like TE77, 72, which are not technically important at all. Now there are also transverse magnetic waves, and those must have both indices non-zero. So out of that we can switch to equations. Again, we have the cross-section. This is the cross-section A times B. And regarding to those mode numbering, we have A, which should have the N, and B, M. So if we name the waveguide mode somehow, this is the M, this should be the N to be consistent with the equation. So we have the M, which comes over here, and the N, which comes over here. So if we have mode TE10, it has 1/2 wave of the standing wave bouncing between those two walls. And that's the convention of naming the modes. So if we now can name the modes, we also are very interested in one important equation, which tells you the minimum frequency at which this mode could propagate between those metallic walls. This is called critical frequency, and the equation for that frequency is just here. The frequency is given as a square root of sum of two squares. The first is the M divided by A, so the number of half waves divided by the length of the longer side of the waveguide. Then you square it and add the N divided by B squared, and then there is C half, where C is the velocity of propagation of light in the dielectric inside the waveguide. So for most waveguides we have air inside, which comes something like 300,000 kilometers per second as the waveguide, as the number we input for C here. Now, as those numbers m and n cannot be zero for simultaneously, so you cannot have a mode TE00. The critical frequency is non-zero for any arrangement. So the waveguide acts as a waveguide only from certain frequency. That's in a good accordance with our everyday life opinion. Our everyday life says, well, okay, there is only one conductor that cannot propagate, but what we think in is the world of direct current. And for DC, the waveguide is not useful because you can't have two conductors. Here there is only one conductor. DC needs two conductors for propagation. But at higher frequencies, beginning from the critical frequency, you can use the waveguide to propagate energy or information. Now, I told, for transversal magnetic modes, you have to get both indices m and n non-zero. From transversal electric, you can have at least one non-zero. That means that the dominant mode, which is the mode with lowest critical frequency, must be TE10. And then you get the critical frequency, and the critical frequency is such a frequency where this would be the 1/2 of the wavelength in free space. Now, as we had the chart before and in last lecture, as we can imagine the wave propagating like bouncing in the waveguide from one wall to the other, we have everything somehow connected through the Pythagoras equation, so that for example, the wavelength that is observed on the enclosure of the waveguide is longer, because that's a projection of the wavelength of the original wave inside, which travels a bit tilted. Depending on frequency, it's quite perpendicular at the beginning. At critical frequency, it's quite tilted at higher frequencies. And this is expressed in this equation. So at any frequency f, if we have a waveguide with a critical frequency fc, we can calculate the wavelength at this waveguide like the wavelength in free space, lambda 0, divided by a factor which is a square root of 1 minus f critical divided by current frequency, and that ratio is raised to the second power. Well, of course, this ratio could be replaced by the current free space wavelength of the propagating wave divided by the critical wavelength, which is 2 times this distance for the TE10 mode. Or, to make things simpler, we can this formulation call f a factor that prolongs the wavelength, for example, but it also is present in other expressions, like if we try to calculate the phase propagation speed, we will find out that it propagates faster than light. That's not against the Einstein's theory of relativity. It is not anything that contains mass or information. It's just, well, a phase is something which is in our thoughts, more or less. So the phase velocity could be higher because the factor f is under unity at propagation frequencies. So we have a phase velocity which is greater than the velocity of light. We get it like dividing the velocity of propagation of light within the material inside the waveguide by the factor f. But it is on the cost of slowing another velocity which is important, and that's the group velocity, which tells us the velocity at which information or mass can propagate, and this is c0 times f. So it's smaller than the velocity of light in open space. The information propagates slower. Yet it might be several times slower, it's still quite fast. Remember that the velocity of light in free space is 300,000 kilometers per second. Now there are also impedances, which is the impedance due to interference of two waves, one, let's say, coming from upside down, one from downside up at any point. The interference changes the ratio between electric and magnetic field. So the impedance is defined in the same way as the wave impedance within free space. It's a ratio of the electric field strength and the intensity of magnetic field belonging to the same wave. And for transverse electric waves, it is the wave impedance Z0 or eta, which is the square root of mu divided by epsilon. So for most cases it's 120 pi ohms. And for transverse electric waves, you can see this is higher than the free space impedance. For transverse magnetic, it's lower than the free space impedance. So this is a set of equations that allow for some calculations within a waveguide. And now I would like to show you a little bit of waveguides. So this is the first sample, a waveguide section. It consists of the waveguide itself, and it has some kind of apparatus for connecting to other waveguides. So in order to have it, for example, connected to another waveguide piece, you just add screws and screw that. For more precise waveguides, this is completed by some metallic rods that allow for very precise connection. And for even more precise waveguides, there is a special type of waveguide flange. It's a little bit larger plane, metallic plane, which has a disruption just a quarter wavelength from the waveguide, which in fact acts as a short, which I will describe you only in the second part of this lecture using a Smith chart. So now this is a waveguide. Of course, you do not need only plain and straight pieces of a waveguide. There are also other waveguide components, like, let's say, a waveguide that is bent 90 degrees so that you can change the direction of the propagation. So this is the bent type, bent piece of the waveguide. Well, which is not the whole history about waveguides. What about not only bending but just tilting it? What is this good for? Well, we have the electric field component in this direction here. And if we need it in that direction, 90 degrees tilted, well, we just can tilt the waveguide. So this is another waveguide piece. And there is an important question: how to get the energy, the wave, into the waveguide? And the reply to that is this component. If you can see inside, there is something like something like an insert, a T, a metallic T, which is now here connected to a coaxial connector. So if you connect here some voltage, it will spread some current inside, and the current flowing down would cause the magnetic field over here to be very similar to the field of the dominant mode that propagates. So this would create, in the waveguide, I have here this insert, it would create two waves, one in this and one in the opposite direction. Because mostly you need the wave to go one direction only, there is a short, let's say a quarter wavelength from that, so that anything that is transmitted in this direction is now reflected here and comes here in the same phase as the input signal. Remember, 90 degrees there, 90 degrees back makes 180 degrees, or 1 pi phase shift, which is antiphase. But by that time of propagation, the phase of the input signal has also changed in 180 degrees, or 1 pi. So this signal is in phase in the signal radiated in the other direction. And that makes this element to be capable to put the energy from a coaxial cable into the waveguide, or to collect the energy from the waveguide and feed it into a coaxial cable. So this is an important part enabling waveguide use. Now, what about something variable? Let's say that we would not need to have variable attenuation. That in that case we would be able to set the propagation of the magnitude of the propagation to be higher or lower. How to do that? Well, I try. You can see inside that I have there something that is moving. It's moving there and back according to a precise position of this screw. I will show for the other camera. Again, I have something that's movable inside. What is that movable? Well, in fact, I have a piece of material that is inserted in, and there are two holders connected to a screw which could precisely position this. Now I will show it here. This happens also, of course, inside. So I can position it to the middle or to the wall of the waveguide. Well, why we do that? Well, that's quite simple. Imagine first that this material is lossy, partially conductive. So if we position it at the wall of the waveguide, remember, the electric field is oriented in this way, but the magnitude for the dominant mode gets to zero because that component of field is tangential to a metallic wall, and it must be zero at the surface of the conductor. So if we place this material just on the wall, it more or less does not interact with the electromagnetic field because it's placed at a position where there already is no field, no electric field. So if that's a partially conductive dielectric or a piece of conductor, it does not change the propagation of the wave. So in this position, the attenuation is zero. Now if we move that into the middle of the waveguide, then the situation is completely different. We have moved a lossy material to the maximum electric field, and therefore there are maximum currents induced by that field in it, and that causes losses. So we have a variable attenuator just by moving this piece of material from the wall to the middle of the waveguide and back. Now, why this is not straight at the end? Why have we bothered to make it, let's say, gradually increasing its dimension in the direction of propagation? Well, if we have made something very straight, there will be a reflection of the wave, but now the wave gradually gets used to the metal insert, and the same at the end. So this is made so to decrease reflection. Now I have shown one possible use. We put this into the waveguide to change the magnitude of the wave propagating, to have a variable attenuation. So this is called a variable attenuator then. In some other cases, we just want to keep the magnitude intact, but what we need to change is the phase of the propagating signal. And now again, we just take another insert which is not lossy, but is a piece of dielectric, non-lossy dielectric. In this case, again, if we put the dielectric to the wall, it will not interact with the propagating wave because the electric field within the dielectric will be zero anyway. And the dielectric is non-magnetic or paramagnetic, so that it does not care for magnetic field. Now, if we move this insert into the middle of the waveguide, then there will be a strong interaction. And remember that within a dielectric, the electromagnetic wave has to propagate slower because this dielectric has greater relative permittivity than the air. So increasing the interaction would slow down the wave, and as we have a precise screw manipulating it inside, we can handle the phase of the signal by setting the distance in the waveguide. That's something that's used to handle magnitude as a variable attenuator or phase as a variable phase shifter, and the arrangement could be like that one I have described now. Well, after talking about this, we sometimes need also a device that is called matched load. We need the wave in the waveguide to absorb and not reflect back. If you just put a metallic closure to a waveguide, you would not achieve that, just the wave would reflect back in full magnitude and cause interference and standing waves on the line. So how to change the energy of the wave into heat? Well, in fact, we have there an insert. I will try to give, it's difficult to look inside, I think, at the moment. Well, okay, a moment. Let's try that again. Well, not much better, sorry. So what is inside is just 1/2 of that phase shifter, or one part of the variable attenuator. So we have there an insert which is conical. It's just in the middle, it's a lossy material, and it gradually eats the wave as propagating inside. So we have there a thin conical piece of lossy material which causes the wave not to reflect back. Now, so far I have shown you elements that are very simple and more or less they are imaginable somehow. There are also elements that would be close to impossible to build up for low frequencies. The first of them would be quite difficult to show, but I can draw it very easily. Just imagine that you have two waveguides like this, placed with the broader wall one on top of the other, and you made a small hole in the middle of one of those waveguides. So I will draw that. We have one waveguide, and there is a second waveguide, and we make a hole here. So if we have a propagating wave here, a small portion of the energy just comes to the other waveguide through the hole and propagates. But due to Huygens principle, this energy would propagate in both directions, regardless whether you send the wave there or in that direction. You would have a small source radiating in two directions. Not a very useful device. Well, but what if I drill two holes that are just 1/4 of a wavelength, each from the other? Now the story is again, I have a wave, for example, propagating in this direction. It puts here a radiation of 1 and second direction. Then the wave reaches the second hole, and again there is a radiation there and a radiation there. Well, it seems that it's the same story still, but it is not. Just look, if the wave propagates this way, then this is the path of the first signal, and this is the path of the second signal through the second hole. Now, you can see that in this direction, both two waves have the same length and therefore phase. So those two waves radiated by the small holes here and we have a result in this direction, which is not the case of the opposite directions. In the opposite direction, the first wave gets just here, and the second wave gets here, but this is 1/4 wavelength, so this is 1/2 wavelength. Those two signals are antiphase. So now we have a special device that if the primary wave propagates this wave, we have a small sample of that wave in this direction, but nothing in this part. On the contrary, if the incoming wave would come from this direction, it will not get here, but it would get here. So this is something that allows us to find out at which direction the main wave in the main waveguide comes. And it not only gets us the information on direction, the result is proportional to the wave that is propagating through the main waveguide. So we call this a coupler, and it can tell us the direction of the wave in the main waveguide. For example, we could, if there is a load that is not matched, then we put input signal. Then we have here the sample of the incoming wave. Here is the sample of the reflected wave. We can put there a detector into each branch, and we can get the standing wave ratio in that waveguide. Now, that would be quite uneasy to build anything like that at DC, our low frequencies. Yes, it would be possible to do something like that, for example, for 50 Hertz, but the dimension of that would be 1,500 kilometers at least in clean air, which is not very practical. So this is a kind of apparatus that is not available at low frequencies but can make its job at higher frequencies. I would like to show you 3 more devices that are specific to waveguide technology. First, I would like to show you a problem that comes out from, let's say, the Thomson's equation. You remember, if we have a resonance circuit constructed from an inductor and a capacitor, think that's both of them are ideal, then the resonant frequency given by the Thomson equation is 1 divided by 2 pi square root of L C, where L is the inductance, C is the capacitor of that capacitor. Now, this is quite a simple equation, so that if you want to tune your circuit to some frequency, you can freely select inductor and capacitor as far as it satisfies the equation. But the equation still holds, but it's not possible to construct any value of capacity or inductor. Just those problems start at a point when you want to get low inductors, just to be somehow in the picture. Professor Thurman, let's say 1920, has established the inductance of a wire, of a single wire which is straight. It still has inductance because it creates a magnetic field around it when there is current in that wire. And that field has the energy, so it must be an inductor. And in fact, you got something for thin wires like those that connect silicon chips to the package, which is a golden wire, let's say 20 or 13 micrometers in diameter. And this kind of a wire has something like 1 nanohenry per millimeter. It depends on the way how you bend it, how you bond it at the ends, but let's say 1 nanohenry per millimeter. And again, if you just have two wires and they just perpendicularly meet each other, so this arrangement would be close to a picofarad. Well, then you get into troubles with low values of inductance and capacity. Moreover, if you have a strong coil and a very big number of turns and the coil is closed, then you have big inductance and most of the field stays inside, which results in a good quality factor. Now, if you just have a low inductor, let's say 1 turn in the air, well, then the field could diminish anywhere. There is some radiation, and the quality factor of such low inductors are very low. I mean, there are companies like Coilcraft that would sell you inductors of 1 or 2 nanohenries ready for surface-mounted devices. But you should bear in your mind that the quality factor could be as low as 5. They can't do miracles. Now, remember, if you have a resonance circuit and you have, for example, the S-curve, which is about frequency, and let's say the voltage on the circuit. So this is at resonance, there is maximum voltage. And we know that the quality factor of that circuit is given by the bandwidth B. So if we divide the critical frequency over the bandwidth, we get the quality factor. And now, we mostly use resonance circuits or filters to filter out one part of the spectra, for example, for amplitude modulation, medium waves, the spectra is 9 kilohertz, the center, and 4.5 kilohertz on each side. And the more selective circuits you have, the more transmitters, stations could broadcast in the band. Now, for today's data communication, you need gigabit speed, which needs broadbands. And in order to do that, you need high frequency. And at high frequencies, you have a problem with the quality factor of your resonance circuit. So you can not cut just a piece of the spectra by a standard thing. But what still works is a cavity has a resonant frequency. And if you polish a piece of waveguide, if you just close this piece of waveguide by two metallic enclosures, you would get a volume that could again resonate. You would get a resonator. And if you cover those walls by well-conductive materials, that is silver, and you fine polish it, you could get high quality factors. So for example, a kind of resonator like this would be this resonator, which is a circular hole, and you have there a piston moving up and down with high precision. You have a precise screw that could position the piston in the proper position. Now you have a small hole inside the waveguide, if you can spot it, a small hole just in the common wall of the waveguide and the resonator. And now this is something that has a quality factor of, say, 60,000. So you can precisely cut a small portion of frequencies by resonators that are created as holes enclosed by metal. And that is something that you can create in waveguide technology. At this frequency band, a similar quality factor made out of inductors and capacitors is impossible. Now I will show you another strange device, which is called insulator. But the word insulator in microwaves has another meaning than has in everyday life. This is a non-reciprocal device. That means that it contains a piece of an isotropic material. You can